Today we will be discussing about Kruskals algorithm. Now I will speak about what a minimum spanning tree is. A minimum spanning tree is a subset of the edges of a connected edge-weighted undirected graph that connects all vertices together without any cycles and with the minimum possible total edge weight. What is Kruskals algorithm? It is a minimum spanning tree algorithm which finds an edge of the least possible weight that connects any two trees in the forest. It is a greedy algorithm in graph theory as it finds a minimum spanning tree for a connected weighted graph, adding increased cost arcs at each step. To find the minimum spanning tree, first we make a subgraph with just vertices from the original graph. Then, from that original graph, we select edges in increasing order of weights of edges while ensuring that a cycle is not formed. This process is repeated until the new graph is connected. Now I shall explain Kruskals algorithm with the help of an example. Here is the graph we will consider for this example. It has vertices from A to I and edges along with their weights. This graph contains 9 vertices and 14 edges. Now we shall arrange the edges in increasing order of their weights. Now we will pick the minimum weight from this order, which is edge GH having weight 1. Next we pick IC as it does not form a cycle, and because it has the least weight amongst the remaining edges. Then we add FG as it has the least weight from the remaining edges and no cycle is formed after adding it. Then we take the edge AB as it has the least weight amongst the remaining edges and no cycle is formed after including it. After that we add the edge CF as it has the least weight amongst the remaining edges and no cycle is formed after including it. Now in the list, GI has the least weight. However, this edge, when included, forms a cycle. Hence, we shall discard this edge. Now we take edge CD, as it has the least weight amongst the remaining edges and no cycle is formed after adding it. The next edge with the least amount of weight is HI. However, this edge, when added, forms a cycle, hence we discard it. Now we add edge AH to the graph as it has the least amount of weight from the remaining edges and adding it does not form a cycle. The next edge with the least weight is BC. However, adding this would form a cycle, hence we discard this edge. Now we take edge ED. No cycle is formed, hence we add it to the spanning tree. Now, since the number of included edges equals the number of vertices minus 1, the algorithm stops here. We have now obtained a minimum spanning tree where the total weight is 37. Now I will be discussing the pseudocode further. First we call a function Kruskal and pass the original graph G as its parameter. Then we create an empty set A to store the edges of the spanning tree. For each vertex V belonging to the vertex set of the original graph, using a makeSet function to store vertices in individual disjoint sets. In other words, if we have n vertices initially, we now have n disjoint sets. Now, with each edge, with vertices u and v in the edge set of the original graph, taken in increasing order of its weight, we use the findSet function to find the set in which u and v belong to. Then, we compare them to ensure they are not in the same set, This is because if they are in the same set, adding an edge would create a cycle. If u and v belong to different sets, we add an edge with vertices u and v to the spanning edge set A. Then we combine sets containing u and v into one set using a union function. Then we will return a minimum spanning tree edge set A. Now we will be discussing the complexity for Kruskals algorithm. In the first step, we create an empty set that will have cost 1, hence its complexity is O of 1. In the next step, we traverse through the vertices of the vertex set of the original graph that will have cost of v. As there are v vertices, the complexity is big O of v. In the next step, we traverse through the vertices of the vertex set of the original graph that will have cost of v. As there are v vertices, the complexity is big O of v. Then, we sort the edges in the original edge set in increasing order of weight. This sort will be implemented using merge sort, hence the complexity is big O of e log e. Now we run the find set operation on the vertices. This takes log v time complexity as we will be using binary search. We will be doing this for e edges, hence the total complexity is e log v. We will now be discussing the recurrence relation T of n is equal to O of 1 plus O of v plus O of e log e plus O of e log v. However, O of 1 and O of v are negligible. Hence, T of n is equal to O of e log e plus O of e log v. The value of e can be at most v squared. Hence, O of log v and O of log e are the same. Therefore, overall time complexity is O of e log e or O of e log v for Kruskals algorithm. We have now reached to the end of our tutorial. I hope you found it helpful. Please do comment, like, share and subscribe for further videos. Thank you for watching.